Hello everyone. So in this video, I'm taking the chapter Atomic Physics and Molecular Physics. And these videos related to atomic physics and molecular physics will be helpful for you in your graduation physics degree, right? UG courses. Next, it is useful for this TG set aspirants, useful for UG NET aspirants and all other competitive exams. So now, in today's video, the first video on atomic physics and molecular physics, let us start with quantum numbers, right? Let us start our first video with quantum right? Quantum numbers. Okay. So now we all know that an atom consists of a nucleus, and around that nucleus in elliptical orbits electrons revolve. Right? Now number of theories came on this atomic structure. As the physics has advanced, now it is said that these orbits or the energy states are quantized. So these quantized energy states, of an atomic electrons are described in terms of quantum numbers. So what are quantum numbers? Quantum numbers are nothing but the quantized energy states of electrons revolving around the nucleus in an atom. So quantum numbers means nothing but the quantized energy states of electrons revolving around the nucleus. Alright? So now here we are having the quantum numbers. The first one, the principal quantum number, right? The second one, orbital quantum number. The third one, spin quantum number, right? The fourth one, total orbital quantum number. Fifth one, magnetic orbital quantum number, right? Sixth one, magnetic spin quantum number. And the last one, seventh one, total magnetic quantum number. So 7 quantum numbers are there. Okay. Now let us discuss about the first quantum number, principal quantum number. Okay. The first quantum number, let us discuss about the principal quantum number. So first, principal quantum number. This principal quantum number is denoted by letter small n, right? And now nucleus is in between the atom. Around the nucleus, electrons revolve in elliptical paths, right? Now these path we term as orbit. So there are number of orbits around this nucleus in which electrons will revolve, right? This principal quantum number explains or gives the information of a principal orbit. It explains about principal orbit. Now, according to Bohr's theory, Bohr named these principal orbits n equal to 1, n equal to 2, n equal to 3, so on. These principal orbits are having non-zero integral values. These principal orbits, they have non-zero integral values. That is, n will be 1, 2, 3, so on. There will be non-zero. These are non-zero. They have non-zero integral values 1, 2, 3, so on. And these are named as K, L, M, so on. So as per Bohr's theory, these orbits, principal orbits or main orbits are named as K, L, M, so on terms or letters. Now next, the number of electrons limited in shell are 2n square. The number of electrons in shell are equal to 2n square. Right? For example, if we take the first orbit, the number of electrons in first orbit is how much? 2. 2 electrons will be there in the first orbit. Right? Now, if we take the second orbit, how many electrons will be there? 2 square n equal to 2. So, 4 into 2. 8 electrons will be there in the second orbit. 2, 4, 6, 8. So on. Right? Each orbit is limited with electrons with formula 2n square. Okay. Now, this is about principal quantum number. Right? Now, it denoted by n. It explains about the principal orbits or main orbits of atom. It has non-zero integral values. That is n equal to 1, 2, 3, so on. These 1, 2, 3 are denoted by K, L, M, N, so on as per Bohr's theory. Now, next, number of electrons are limited in each orbit and using the formula 2n square by following the formula. So, for example, if we take n equal to 1, we will have only 2 electrons, n equal to 2, 8 electrons, and n equal to 3, what we will have? 18 electrons, so on. So, this is about the principal quantum number. Now, next, let us go for the second quantum number, orbital quantum number. Okay, orbital quantum number. So, orbital quantum number. So, this is denoted by small letter L. And this explains about the nature or the shape and nature of orbit. And also, it explains about the orbital angular momentum. Alright. It explains the shape of orbit and also orbital angular momentum. Right? Now, next, it has non-zero integer values. It has 0 integer values, 0, non-zero, all integer values. That is, L starts with 0, 1, 2, 3, so on. Now, Sommerfeld named this 0, 1, 2, 3 with a small letter S, P, T, F, so on. Okay, Sommerfeld named it as S, P, D, F, so on. Okay, so now it is denoted by L. It explains about the shape of orbit and orbital angular momentum. Right? of an electron orbiting in around the nucleus. It has a 0 integer values also. So L equal to 0, 1, 2, 3. And they are represented by S, P, D, F, so on. Alright. Now next, here in orbital quantum number, for example, this orbital number, quantum number, is nothing but equivalent to, it explains, or it is, what we will say, it gives the information about it, the complete structure of principal orbit. Right? Actually, according to the Sommerfeld theory, the principal orbit is again divided into suborbits or subshells. So this orbital quantum number explains about the subshells present in principal orbit. Right? It explains about the subshells present in a principal orbit. And the number of these subshells is equal to number of principal orbit. How means, for example, L equal to 0, it belongs to principal orbit 1. L equal to 1, it belongs to the second orbit. So in second orbit, the L equal to 0, 1. It belongs to second orbit. The third orbit, number 3. So how many subshells will be there? 3 subshells will be there. 0, 1, 2. Now N equal to the fourth principal orbit. How many subshells will be there? 0, 1, 2, 3. I think you understood. The number of subshells will be equal to the number of principal orbit. For first principal orbit, only there will be no subshells. The orbit itself will be there. For the second principal orbits, 2 subshells will be there. Third principal orbit, 3 subshells, so on. In such a way, the subshells will be present in the principal orbit. And this orbital quantum number explains about that subshells present in the principal orbit. Right? Now, next step, here, the orbital angular momentum is written as orbital angular momentum is written as PL is equal to LH by 2 pi. In wave mechanics, this is as per classical mechanics. Now, as per wave mechanics, the L is replaced by under root L into L plus 1. The L is replaced by under root L into L plus 1. Okay. So, as per wave mechanics, we write it as the orbital angular momentum is written as under root L into L plus 1 H by 2 pi. Right. Now, next, this orbital quantum number not only explains the shape of the orbit, not only explains the orbital angular momentum, and not only explains the subshells present in the principal orbit, but also it governs the bond present between the electron and the nucleus. Okay, it also gives or explains or it governs the, now here the nucleus is there, electrons are revolving here in such a way around the nucleus. Now this is N is equal to 1, only one, no subshells are there in the first orbit, principal orbit. So this is very close to the nucleus compared to this electron which is present in the second orbit. So the attraction or bonding between electron and nucleus will be more when L is equal to less. The the attraction or bonding between the electron and nucleus will be more. When L is equal to less, it will be more. As L goes on increasing, the bonding between the electron and nucleus also decreases. Inversely proportional. As L is less, the bonding between electron and nucleus is more. As L is more, the bonding between electron and nucleus will be less. Right? So it explains about this bond between the electron and nucleus also, or it governs the bond between the electron and nucleus. Now next, as per Sommerfeld theory, this orbital quantum number is equivalent to Sommerfeld's azimuthal quantum number. So this orbital quantum number is nothing but similar to the Sommerfeld's azimuthal quantum number, and it is written as L is equal to n pi minus 1, where n pi we call it as azimuthal quantum number. Right? Now this is about the orbital quantum number. Now next, let us go for the spin quantum number. Hope you understood. One, it explains about the shape of orbit, orbital angular momentum, explains about the substance present in the main orbit, also governs the bond between the electron and nucleus. Right? If L is less, the bonding will be more. If L is more, the bonding will be less between electron and nucleus. And now it is having the zero integral values also. It starts from 0, 1, 2, 3, so on. Now these are represented by the letters S, P, D, F, so on. Right? Now next, here L equal to 0, the number of subshells are equivalent to the number of principal quantum. Principal quantum number, if it is 1, number of no subshells. If it is for second principal orbit, we are having 2 subshells. And another thing I forget to say, if L equal to 0, we call it as S orbital or S subshell. S subshell or S orbital. If L equal to 1, what we will call P subshell. If L equal to 2, T subshell. If L equal to 3, F subshell, so on. These are represented as the spectral notations. For L equal to 0, S. L equal to 1, P orbital. L equal to 2 means D. L equal to 3 means F. So this is about orbital quantum number. Now next, let us move for spin quantum number. Right? The third one, spin quantum number. It is denoted by S. It explains about the spin of electrons. Orbital quantum number explains about the shape of orbit. Also the orbiting of electron. Orbiting of electron means the movement of electron around the nucleus in an orbit. Right? Now the electron not only orbit along the nucleus. First, the electron orbit around the nucleus. At the same time, while orbiting, electron spins around itself and orbits. Right? It spins around itself and it orbits around the nucleus. Right? So that spinning of electrons is explained by spin quantum number. The spinning of electrons is explained by spin quantum number. Right? Now here only 2 spins are possible. One is clockwise spin, other is anti-clockwise spin. So spin quantum number has only 2 values. One is plus half, other is minus half. It has only 2 possible values. One is plus half, other is minus half, depending upon the direction of a spin, either clockwise or anti-clockwise. Right? Now next one is total angular momentum. Right? The next one is the total angular momentum. So already the word itself is saying total orbital quantum number, sorry. So total, or you can also say total angular quantum number. It is denoted by J. It is denoted by J, right? Capital J or small j. It is denoted by J. It explains about the orbiting motion as well as the spinning motion of electron. It explains about the combined effect of orbiting and spinning of an electron. And so this is written as L for orbiting, S for spinning, or we use small letters, so let us write as a small letters L, S, right? The another main thing what this explains is, it explains not only the orbiting and spinning motion, mainly it explains the splitting of spectral lines. The main feature is, it explains about the splitting of spectral lines, right? The splitting of spectral lines. In more detail, let us go, I will explain in the future videos about the splitting of spectral lines, right? It explains about the fine, or we can say the fine structure of spectral lines. Fine structure means splitting. The fine structure of spectral lines. So now here, it has some selection rules. Not all lines are possible. Only few spectral lines are possible for transition. Not all transitions are possible. Only few transitions are possible. When electron jumps from one orbit to the other orbit, right? Electron, when jumps from one orbit to the other orbit, not all transitions are possible. Only few transitions are possible. That few transitions are given by selection rules. In my future video, let us discuss about these selection rules also. And the selection rule for this total angular momentum is less or minus 1 or 0. The selection rules for this total angular momentum is plus or minus 1 or 0. So this is about total angular momentum. Now next, let us move for magnetic orbital quantum number. Okay, magnetic orbital quantum number. Okay, now this is denoted by ml. M subscript n, denoted by ml. Then why this magnetic orbital quantum number? Why means, when we take the atom and place it strong electric field. Now place the atom in strong electric field. We will find that there is a slight difference between the L values, right? The L and as well as the N values of the electrons, sorry. It explains about when we place the atom in a strong electric field, the electrons with the same N and L values shows a slight difference between each other. The electrons having the same N and L. N is principal quantum number, L is orbital quantum number. When we place an atom in a strong magnetic field, the electrons having the same values of N and L will show a slight difference between themselves. Now, in order to understand about that only, the magnetic orbital quantum number is introduced. So magnetic orbital quantum number explains about that slight difference of electrons having the same N and L values when placed in a strong magnetic field. Already before this only, Zeeman has explained about the splitting of spectral lines in magnetic field, and Stark has explained about splitting of spectral lines in electric field. Now this quantum number gives the more details about that particular difference. Okay. Now next, here let us take now also as per the rules of space quantization. So L with H is magnetic field, will be limited the orientation of L. What is the meaning of orientation? Orientation means indicating about the different positions or the directions of a particle. The particle has knowing the orientation means we are knowing the different positions of that particular electron, right? So now the orientations of L with H are limited, right? Now this orientation of L with the field direction, we call it as magnetic orbital quantum number. The orientation of L with the field direction, we call it as magnetic orbital quantum number, right? Now let this be the field direction. Now I'm taking the L in such a way that it makes an angle theta with the field direction. Now the orientation will be in such a way, right? In such a way. The dotted lines indicates the orientation of L along the field direction. It gives nothing but the magnetic orbital quantum number. Now for example, now here this is L and this gives the magnetic quantum number, no? Orbital quantum number. Now from this, what we will write? Cos theta is equal to ml by L. So ml value will be equal to L cos theta. But ml must have integer values. It must have integer values, right? So means it must have 0, 1, 2, so on. And cos theta never exceed unity. 1 ml must have integer numbers. Cos theta never exceeds unity. So the values of ml changes from plus L to minus L. So how means 0, plus 1, plus 2, so on. So, sorry. How we will write means 0, 1, minus 1, so on, minus L minus 2, minus L minus 1, and this side plus L minus 2, plus L minus 1, so on. In such a way we will write the values. Let us take some examples. So now there will be 2L plus 1 possible ml values, we can say possible ml values. Now let us take one example of when L equal to 0, ml will be 1. 0 is substituted. Means here it is having only one orientation. It is having, the electron is having only one orientation. Each value of principal quantum number n, there is only one orientation, and that is s orbital. Now x-axis, y, z-axis, right? S orbital, spherical shape, s orbital, right? P orbital, dumbbell shape. Okay, in chemistry you have read. Now next for L equal to 1. If I substitute 1, what happens? 2 plus 1, 3. So 3 orientations are possible. What will be that? 0 plus 1 minus 1. 3 orientations will be there. Alright? So 0 plus 1 minus 1. How will be that? Now L equal to 1 means, here I will write L equal to 0 means S, 1 means P, 2 means D, so on. So orientations 0. 3 axes I am taking. Now plus 1. 1 will be in such a way. Now minus 1 in such a way. P orbitals dumbbell shape, and in such a way we will have 3 orientations. Similarly, if we take L equal to 2, substitute 2, 2 2s are 4, 4 plus 1, 5. So what you will get? Minus 2, minus 1, 0, plus 1, plus 2. So 5 orientations will be there. Right? Or before I got now. For this 1, right? 2, 3 in such a way. The orientations of electron for L equal to 1. So now next step. For example, if magnetic field is absent, up to now we explained in the presence of magnetic field. Now if magnetic field is absent, then here 3 orientations, right? Here the energy of all will be same. They will have same energy. So same energies means what we will call, or we can say that all these 3 orbitals will have same energy. Right? Here the orientation of orbitals. Here 1 orientation, here 3 orientation, orbitals will have 3 orientations, here 5 orientations, same. So on. So if magnetic field is absent, then all orbitals will have same energy. The orbitals with the same energy, we call it as degenerate orbitals. Right? We call it as degenerate orbital. Now this we call it as threefold degenerate orbitals. This we call it as fivefold degenerate orbitals. Right? Now this is about magnetic orbital quantum number. Next step, magnetic spin quantum number. Now this explains about the spin of vector along the projection of spin of vector along field direction. The projection of spin of vector along field direction. And the last one is the total magnetic quantum number. It explains about the magnetic orbital quantum number plus spin orbital quantum number. The combined effect of these both we call it as the total magnetic quantum number. So these are the 7 quantum numbers. Right? So thank you for watching my video. If you like it, share it, subscribe it. Yours, Reshma.